In this video, we will talk about independence. So I want to begin with an example which says that you roll two fair dice, a blue die and a red one. The event E is the sum of the rolls is greater than 9. The event F is the blue dice is a 5. Find the following probabilities. Part A asks for the probability of E occurring, that the sum of the rolls is greater than 9. So because we're rolling two dice here, and we're interested in what their sum is, let's make a table of possible sums based on the rolls that we see. So for one of the dice, I'm going to write 1, 2, 3, 4, 5, 6. And then for the other one, I'm also going to write 1, 2, 3, 4, 5, and 6 just horizontally. Okay, let's give ourselves a little bit more room here. So I'm going to move this down. So I'm going to say that these values on the top, these represent the red die, whereas the values on the left represent the blue die and what gets rolled from the blue die. Okay, so now I'm going to make a table, so I'll draw some lines. So some vertical lines this way, and then horizontal lines across. Okay, so there we go. We have this table. And now within the table, let's write the sum of the value that we see on the left from the blue die and the value that we see on the top from the red. So in this section, we are going to add this one with that one, so the sum is a 2. In this region over here, we're going to sum this 1 with that 2 above, which gives us a 3. Similarly, if I go down diagonally over here, now we're summing this 2 with that one, which gives us a 3. And we can continue in this way to fill out the table. I'm going to do one more of these diagonals slowly, and then hopefully I think we'll start to see a pattern. Okay, so if I go down here, I'm summing a 3 and a 1, which gives me a 4. Over here, I'm summing a 2 and a 2, which gives me 4 as well. And then here, I'm summing a 1 and a 3, which also gives me a 4. So it seems like on each diagonal, I go up by 1. That seems to be the pattern. And you can verify this, but it turns out it is true. So on the next diagonal, I'll write a bunch of 5s. 5, 5, 5, 5. Next one is going to be a bunch of 6s. 6s. And the next one will have a bunch of 7s. Let's just verify one of these. Over here, I'm summing a 6 and a 1, so that is a 7. In fact, all of these on this diagonal will be a 7. The next diagonal will all be 8s. A bunch of 8s. Next diagonal will be 9s. 9s. Next one will be 10s. Next one will be 11s. And then finally, when you sum the 6 and that 6, we get a 12. Okay, so it was nice to be able to see that pattern there. It helped make filling out this table a little bit more quick. Okay, so part A is asking for the probability that E occurs, that the sum of the rolls is greater than 9. Okay, so I'm going to set up a fraction for my probability, and on the top, I'm going to count the number of ways for the sum to be greater than 9. And on the bottom, we're going to count the number of total outcomes. Okay, so total outcomes, I could count them in my table. There are 36 total outcomes within this table. One way I could have seen that a little bit more quickly is that 36 we can also obtain by saying, wait, for the first die, there are 6 choices for the roll. And for the second die, there's also 6 choices. So 6 times 6, that is 36. So how many of these have the sum being greater than 9? Well, that's these 3 10s, the 2 11s, and this 12. So there are 6 outcomes where that happens. And I could simplify this by dividing the top and the bottom both by 6. And doing that, we get 1/6 for our probability. Alrighty, let's do part B, which is asking what's the probability of F occurring? So remember, F was the event that the blue dice is a 5. Okay. So the probability that F occurs, I could set it up in the same way. On the bottom, I'll have the number of total outcomes. And on the top, I could count the number of outcomes where the blue die will be, is it a 6 or a 5? Is a 5. The blue die is a 5. So total outcomes we already know is 36. So how many outcomes are there where the blue die is a 5? Well, looking at my table, that's this whole row. So there's 1, 2, 3, 4, 5, 6 ways for the blue die to be a 5. So I get the same thing actually. So, and I know this already simplifies to 1/6. So this probability is also 1/6. All right, let's do part C now. C is asking, what's the probability of E intersected with F? So now we're going to need E and F to both happen. So recall what E is. E is the sum of the rolls being greater than 9. F is the blue dice being a 5. Sorry, one other thing I wanted to point out about the probability of F was, to find the probability that the blue die is a 5, I actually didn't even need to consider the red die at all. I could see that, wait, there's a 1/6 chance for the blue die to be a 5, and I could have also said the probability, that probability is 1/6 in that way, and that would have been a little bit quicker. Okay, so for C, we want the intersection of these two and that probability. So pause the video for 1 minute to try this one on your own first. I'm going to zoom it out a little bit so you can see what E and F are as well as this table, and then try this one on your own. 4, 3, 2, 1. Pause it and try this one for about 1 minute. Alrighty, so hopefully you've done that. Hopefully you paused it and tried this for about a minute. Let's talk about it together. So we want the probability of E intersected with F. So on the denominator again, we need to count the number of total outcomes. And in the numerator, we're going to count the number of ways for this intersection to happen. So for E to happen, we need the sum to be greater than 9, and, because the intersection after it, and, for F to happen, we need the blue to be equal to 5. Alrighty, so we know the total number of outcomes. Total number of outcomes is 36. So now I'm going to go to the section where the blue was a 5. So that is this row. And I want to know in that section, how many outcomes are there where the sum is greater than 9? So the sum is greater than 9 if it's a 10 or if it's an 11 in this row. So there are 2 outcomes like that. Okay, and I can simplify this by dividing the top and the bottom by 2. And doing that, we will get 1/18 for this probability. Okay, so at this point we are ready to state a key definition. So this definition says that events A and B are independent. So independent if the probability of A intersected with B is equal to the probability of A times the probability of B. And I'm going to highlight this. This is a key definition from this section. There's also an equivalent way for me to write this. So if I rearrange this to get probability of A by itself, we would get it equals probability of A intersected with B divided by probability of B. And now this right-hand side is a conditional probability. The right-hand side has now become the probability of A given that B occurs. So we can also say that A and B are independent if the probability of A occurring is equal to the probability of A occurring given that the event B occurs. Okay, and this alternate way of stating what independence is gives us a more conceptual explanation of what independence really is. What this is saying essentially is whether B occurs or not does not affect A's chances of occurring. Okay, so I'm going to highlight this one as well. A and B are independent if the probability that A occurs is equal to the probability of A given that B occurs. So in the beginning, now that we've stated this definition, when we test whether two events are independent or not, we're going to apply one of these formulas and see if it holds. And if it does hold, that means the events are going to be independent. Eventually, we'll be able to see that there are some scenarios where it's fairly obvious and clear to tell that the two events are independent even without doing this mathematical check. And we'll see that a bit more in later sections. All right, so the final part of this example, D asks, are E and F independent? So let's check it using one of our formulas. So let's check to see if the probability of E intersected with F is equal to the probability of E times the probability of F. And let me put a question mark above my equal sign because I don't know if they're going to be equal just yet. So we found each of these probabilities. For the intersection, it was 1 over 18. Oh, let's write that better, 1 over 18. And on the right-hand side, both of these probabilities were 1/6. So we get 1/6 times 1/6. And if we multiply those, this is 1 over 36. So clearly those two things are not the same. 1 over 18 is not equal to 1 over 36. So these two events are not independent. They are not independent since the probability of E intersecting F does not equal the probability of E times the probability of F. So if we had wanted to, we could have also checked it using this formula. The probability of A needs to be equal to the probability of A given B. But in our problem, it was easier to use the first formula because we already had all three of these probabilities. Whereas to use this second formula, we would have needed to figure out what this conditional probability is first. So that one would have been a little bit more work. So in the next video, we will do another example where we test for independence that involves a table of values.